So let's get started. I'd like to tell you about my group's research in one particular area. So broadly speaking, my group is interested in the rational design of homogeneous transition metal catalysts. And the way we do this is we try to adopt a strategy which involves understanding the mechanism of reactions. And this can mean understanding the elementary steps involved in the reaction. This can mean understanding activation of a precatalyst. This can mean understanding decomposition pathways. And we do this by making model complexes, doing kinetics, doing competition experiments, and in some cases, using computational studies. So some of the target reactions that we study in my group include transformations related to finding liquid organic molecules for hydrogen storage. So these will be molecules that release H2 on demand, or incorporating CO2 into both commodity chemicals or organic molecules. The topic that I'm going to focus on today is the development of new precatalysts for cross-coupling. The talk is going to be in 3 parts. In the first part, I will very briefly expose you to an applied area where our mechanistic studies have led to an actual precatalyst. In the other 2 topics, which will focus on nickel as opposed to palladium, I will really go into more detail into what our mechanistic approach entails. Of course, I didn't do this work by myself, so here is the team. Typically in the group, we have 1 graduate student working on nickel and 1 graduate student working on palladium at any given point in time. One of my students, Matthew Espinoza, and I'll show some of his data today, is here. I need to say very good things about him because he is driving me back to New Haven later this evening. But he is an excellent student, and he has been working with collaborators directly at Umicore. We have a variety of other collaborators who help us with, for example, EPR spectroscopy and DFT, and along with people at Umicore, we've had a number of other industrial collaborators who have kind of told us, Nilay, you're on the wrong track, this is not interesting, this is actually what we care about. So we'll start by talking about our rational design of new precatalysts for palladium catalyzed cross-coupling. And to this audience, I am not even going to give an introduction to cross-coupling. What I am going to say is, why do we need precatalysts? And we can understand the need for precatalysts by looking at the classic cycle for palladium catalyzed cross-coupling. And numerous people have done work for a very long time to elucidate these elementary steps. They involve a monoligated palladium zero active catalyst which undergoes oxidative addition with the electrophile, transmetallation with the nucleophile, and then reductive elimination to generate your CC bond-formed product. Now, this active catalyst is monoligated palladium zero, and people have developed highly specialized ligands which stabilize the palladium zero and also facilitate the elementary steps in cross-coupling. These ligands now have, in many cases, comparable price to the palladium. And what this means is that the traditional method for introducing your palladium and ligand into the catalytic cycle, which involve taking palladium zero and excess ligand, is no longer desirable. If you do this, you will have excess of an expensive ligand, and also your active catalyst is monoligated palladium zero. If your active catalyst is monoligated palladium zero, you don't want more ligand in there because this creates off-cycle equilibria. What this has meant is that over the last 20 years, there's been a shift to using well-defined palladium-2 precatalysts, which already have a 1-to-1 metal-to-ligand ratio. What are the qualities that we want in a precatalyst? You want a precatalyst that's easy to synthesize. If it takes numerous steps, it's going to be expensive and it's not going to be practical. The catalyst needs to be stable, or the precatalyst needs to be stable. And what I mean by this is that you want to make it, and 2 years later you want to be able to take it off the bench, and it's going to give you the same catalytic activity as the day that you made it. This activation from palladium-2 to palladium-0 needs to be achieved with mild reagents, preferably the reagents which are already in your cross-coupling reaction, such as base. You need rapid activation. If your cross-coupling reaction needs to go in minutes at room temperature, activation needs to take seconds. And you need a high yield of palladium-0 after activation. Otherwise, you're wasting both your ligand and your metal. There are a number of commercially available precatalysts, and I'm not going to talk about all of them today. I'm just going to highlight one example which led to our work in the field. And this precatalyst was initially developed by Steve Nolan's group, and it features an allyl ligand, a palladium-2 center, a chloride, and an L, and traditionally L has been an NHC ligand. In the last 4 or 5 years, Thomas Collicott has shown that this can also be a phosphine. This is air and moisture stable. It has a well-defined ratio of metal to ligand, and it's easy to use in high-throughput experimentation for reasons I'll show you at the end of this slide. What was in the literature when we started our work was that the nature of the substituent on the allyl group makes a large difference to catalytic performance. If we look at this simple Suzuki-Miura reaction, you can see that when I have an unsubstituted allyl ligand, I get 12% yield after 1 hour. In contrast, when I have a phenyl group on the allyl ligand, known as a cinnamyl ligand, our yield is 90%. So a small difference to precatalyst structure makes a large difference to catalytic activity. And what this has meant is that this cinnamyl type species is extensively used in catalysis. And you can get the cinnamyl type species as this unligated dimer. And this unligated dimer is very useful for rapid screening via HTE, because you can add the ligand of your choice to get to the precatalyst, which will then go on and do catalysis. What we were interested in is from a fundamental level, why is cinnamyl so much better than allyl? How do we explain the difference between the two? This was the work of my first PhD student, Damien, and I'm going to summarize 3 or 4 years of hard work in about 30 seconds. What Damien showed was that the reason the cinnamyl system is more active than the allyl system is because we have an off-cycle competing dimerization of our precatalyst. So you start with palladium-2 and it's reduced to palladium-0. However, this palladium-0 can either undergo oxidative addition with the substrate to enter the catalytic cycle, or it can undergo a comproportionation reaction with palladium-2 to form a palladium-1 dimer. And this palladium-1 dimer, which we isolated and crystallographically characterized, is not catalytically active. So anytime you form it, you're wasting both your ligand and your palladium. It transpires that when you have an unsubstituted allyl ligand here, about 80% of your palladium goes to this inactive palladium-1 dimer. Whereas when you have cinnamyl, that number is only 35%, and that explains the increased activity of cinnamyl versus allyl. But 35% of our palladium is being wasted. So the question becomes, how can we use this information to design a better precatalyst? And from our mechanism, we can see that there are 2 ways to do that. One, we can make this barrier for comproportionation even higher. Okay, so we kinetically inhibit the formation of dimers. 2, if we increase the rate at which we go from palladium-2 to palladium-0, there will be less palladium-2 present to undergo the comproportionation reaction. We use this information to design an improved precatalyst, and this precatalyst features this 1-terp-butyl-indenyl ligand and is shown here. Again, it comes as an unligated dimer, and you can add the ligand of your choice to make the palladium-2 1-T-butyl-indenyl L chloride. We've scaled up this synthesis, and you can do it on fairly large scale. So what are the types of ligands that we can use? We can use all of the common NHCs, and we can use most of the common phosphines, including the Buchwald type phosphines. Okay, so this precatalyst has an advantage over many other precatalysts that are available in that it's compatible with both NHC and phosphine ligands, which is very useful for rapid ligand screening. We've shown that it's highly active for a number of different type of reactions that you might be interested in. So these include the standard types of cross-coupling, Suzuki-Miura, Buchwald-Hartwig, alpha-arylation. And it's also compatible with non-traditional electrophiles, so you can move away from aryl chlorides and you can use things like aryl esters, which are kind of the state-of-the-art newly developed cross-coupling reactions. So I'm going to do something in this talk which I have never done in public, which is to show you 2 slides of comparative data. Okay, normally we try not to show comparative data where we directly compare precatalysts, because the problem is you need to be very careful that you're doing a fair comparison where you're testing different precatalysts under the same conditions. So firstly, I'm going to show you a precatalyst comparison where we use our precatalyst supported with the IPR ligand, so this is an NHC, and here are some other types of precatalysts which you might use with NHC ligands. One of them comes from Mike Organ's group and is the Pepsi precatalyst. We're looking at the reaction under 2 different conditions, with T-butoxide, which is kind of a strong base, and with potassium carbonate with a weak base. And you can see that under these conditions, our precatalyst gives improved performance relative to all of the other precatalysts. This is especially true in comparison to the cinnamyl or crotyl precatalysts, which are commonly used. If I change the ligand and I look at an XPhos-supported precatalyst, I can now compare the precatalysts to, say, the Buchwald G3 systems. And now comparison becomes extremely challenging because the Buchwald precatalysts are typically used under different conditions to what our precatalysts are used. Nevertheless, condition C corresponds to the Buchwald type systems, and you can see you get a very large increase in G3 when you run it under those conditions. And you can see that our precatalyst compares very favorably to the other systems when we compare it like this. So this conclusion should not be that our precatalyst is always better. It's simply showing you that here we have some examples under different conditions where our precatalyst is performing very well. For that reason, the precatalyst is commercially available, so both from STREM, and I know that Albani is here, and probably what's been more exciting to me is over the last 3 or 4 years, we have collaborated with Umicore to make the catalyst available on a very large scale. So I am a small person, Ralph and Eileen are kind of normal-sized people, and I'm always blown away because this is the reactor, and you can see that the reactor is certainly much bigger than Ralph or Eileen. Also, this poster here is bigger than me. I would argue, though, that it is really the fundamental mechanistic study that we did which enabled us to develop the new precatalyst. Okay, and in this section of the talk, I didn't talk in detail about the mechanism. As we transition to nickel, I'm going to give you more of a flavor of the fundamental studies that my group does. Okay, so why might we be interested in nickel? I'm sure some of the other speakers later on will also talk about this. It's because it's significantly cheaper and it's more abundant than palladium. So potentially it would be more sustainable if we were to do catalysis using nickel. I would argue that it also offers us new opportunities for reactivity. There are things or substrates that we can activate with nickel that we can't activate with palladium, and I've shown some of these substrates here. Additionally, from a mechanistic viewpoint, the mechanisms of nickel-catalyzed cross-coupling are nowhere near as well understood as those for palladium. And this gives us an opportunity to try and make real advances using the same types of mechanistic studies that we've done for palladium. And again, the goal is to rationally design improved systems. Our work in this area started when we saw this report from John Hartwig's group. He had used this DPPF-supported nickel cinnamyl chloride species to cross-couple a wide variety of heteroaryl boronic acids and also chlorides and bromides. And the conditions for this reaction caught our attention because they were very mild and very low catalyst loading for nickel. Traditionally, nickel-catalyzed cross-couplings need far higher catalyst loadings than palladium, and John was able to do this using 0.5 mol% catalyst. More interestingly to us, look at the structure of his catalyst. It has the cinnamyl group, which we had just spent so much time understanding for palladium. And we wanted to see if what we had learnt for palladium would translate to nickel. What is the speciation of nickel during catalysis? Are we forming nickel 1? The first experiment that we did involved this cross-coupling using a naphthyl chloride and a boronic acid, and we tried to identify the nickel using 31p NMR spectroscopy because we have a ligand which is 31p NMR active. We saw nothing in the spectrum. Nickel can form odd electron oxidation states and monomeric odd electron oxidation states, which meant that we could use EPR spectroscopy to try and understand what was present in solution. And we saw this really quite intense signal, and a significant amount of our nickel was in this paramagnetic form. 30% after 30 minutes, 70% after 1 hour. We were able to identify this paramagnetic species as this nickel 1 chloride. So we knew it was being formed, we didn't know whether it was a good thing or a bad thing. To try and understand that, we synthesized a series of nickel precatalysts in the 0, 1, and 2 oxidation states. And these are shown here. And to our amazement, they all gave roughly the same catalytic activity. Didn't matter what you put in there, they were coupling this reaction with the same efficiency. And additionally, all of the nickel 0 and nickel 2 precatalysts generated a significant amount of the nickel 1 species during catalysis. They all gave appreciable amounts as detected by EPR. The nickel 1 species appeared to stay in the nickel 1 form. Now, our preferred precatalyst of the 5 that are up here is this orthotoluene nickel 2 chloride. This is one that Seb has worked on, and the reason we like this is that it's air and moisture stable. It has a synthesis which doesn't involve nickel biscod. Nickel biscod is actually quite expensive. It's comparable to palladium in price, and it's commercially available. The first person to report this was actually Steve Buckward's group at MIT. So we didn't know if nickel 1 formation was good or bad. All we knew was that it was happening. And so we needed to try and understand that by ascertaining what the role of nickel 1 was in catalysis. The answer to this was actually serendipitous. We changed our substrate from a aryl chloride to kind of an aryl sulfamate. And this is chemistry that was pioneered by Neil Garg, amongst others. These can serve as traceless directing groups for CH bond activation. And when we used the Buckward type precatalyst, we could couple a wide variety of these at sort of room temperature or more mild conditions. Under these conditions, the nickel 1 species is not catalytically active. Nevertheless, when we use this orthotoluene nickel 2 chloride precatalyst, we form it in significant quantities. So this tells us that that nickel 1 chloride is an off-cycle or decomposition species. You need to avoid forming it in catalysis. So the question becomes, if we want to stop forming it in catalysis, we need to understand how it's formed. So how is it formed? Here is our proposed catalytic cycle. We propose this reaction involves a standard nickel 0, nickel 2 cycle. The same as for palladium, here are the steps. But as with palladium, incomplete activation of our precatalyst leads to the formation of nickel 1. So essentially, the nickel 2 can comproportionate with the nickel 0, and it sends us across to this pathway here, where we generate a nickel 1 aryl and a nickel 1 chloride. And it's this nickel 1 chloride that we synthesized and identified by EPR spectroscopy. We proposed that these nickel 1 aryls decompose to generate these arenes, which we detect by GC. Additionally, when we look at the EPR spectrum of these reactions, we see that it contains two signals. And there is another place in our catalytic cycle where we can generate off-cycle nickel 1. This involves comproportionation between the nickel 2 product of oxidative addition and nickel 0. And again, it generates an unstable nickel 1 aryl, but in this case also a nickel 1 sulfamate, which we verified in stoichiometric reactions and identified in situ by EPR. This process does not happen to a great extent in catalysis. If it did, we would be consuming our substrate and our yields would go down. Additionally, the other way you can stop that process from happening is by increasing the number of equivalents of boronic acid. And a dirty little secret of nickel-catalyzed cross-coupling is people get high yields because they use a large number of equivalents of boronic acid. And here is the reason for that. It stops the formation of these off-cycle species. Finally, this species could also undergo comproportionation in principle, but it doesn't, because intramolecular reductive elimination is faster than bimetallic comproportionation. I would say the only aspect of this mechanism that I haven't shown you convincing evidence for is the formation of these nickel 1 aryls. And these nickel 1 aryls have been proposed to be present in a wide variety of nickel-catalyzed cross-coupling reactions, more than those involving sp2 hybridized substrates, but sp2, sp3 hybridized substrates, reductive carboxylation. So we were able to show that if you took a nickel 1 halide and you react it with a Grignard reagent, you could form nickel 1 aryls. And depending on the steric bulk of the aryl substituent, the nickel 1 aryl could be extremely unstable. So just a phenyl substituent has a lifetime of less than 5 minutes at minus 90 degrees as determined by EPR spectroscopy. Or if you have a very bulky aryl group, you could get essentially indefinite lifetime. With these fairly bulky aryl groups, we were able to crystallize these species, really unequivocally confirming that they are present and possible. We could show that if you use these as precatalysts, they first go to nickel 0 and then you go into the catalytic cycle, consistent with our mechanism, which shows that in this case, the nickel 1 is off cycle. Okay, so what I've shown you here is that several common nickel precatalysts generate nickel 1. In these cases, nickel 1 is detrimental to catalysis. We are hoping to use these studies to design a more efficient cross-coupling catalyst. We have not been able to do that yet. What we need to do, in our opinion, is change the nature of this aryl group to stop the comproportionation from happening. We can't really change the ligand because the ligand is integral to these elementary steps, and we also have limited choices with our halide, so we're working on that at the moment. I introduced nickel by saying one of the things we're interested in is using nickel to catalyze reactions that palladium cannot. And I would say that one of the most topical and interesting reactions that nickel can catalyze at the moment that palladium cannot is cross-electrophile coupling reactions. And cross-electrophile coupling reactions are ones which, instead of having an electrophile and a nucleophile, you have two electrophiles. As I said in the introduction, my group has an interest in using CO2 as a substrate, and for that reason, we started our studies in this area by looking at a cross-electrophile coupling reaction that involves CO2. So one of our electrophiles is an aryl chloride, and the other is CO2. And I'm showing you a report from Suji's group in Japan, where they'd shown that this nickel 2 precatalyst with a variety of different additives could take an aryl chloride to a carboxylic acid. You'll note the need for manganese in these reactions, and that's because you need a stoichiometric reductant to balance the stoichiometry. This reaction has been extended, in particular by Ruben Martin's group in Spain, to a really large variety of substrates, including alkyl halides, and he's also shown examples where you can chain walk and really functionalize sites which are remote to the initial substrate. But this reaction has limitations, which mean that it's probably not viable to be used at this stage. And in fact, many cross-electrophile coupling reactions, and we're just studying one example at the moment, have these limitations. The first is probably not that important because nickel is cheap. You need a high catalyst loading. Additionally, you need a large number of additives. You can look at the list of reagents here, and we don't always know what these additives are doing. Perhaps more troublingly, these reactions tend to only work in undesirable amide-based solvents. So this reaction works in DMI, which until we read this paper, I probably couldn't have told you what the structure is. More commonly, they run in DMF, DMA. And you also need a super stoichiometric amount of this heterogeneous metallic reductant. And that makes scale up difficult because you end up with irreproducible kinetics, which are not desirable when you're trying to run in a reactor. When we started our work, this was the proposed mechanism for nickel-catalyzed reductive carboxylation. You start with nickel 2, it's reduced to nickel 0. Then your substrate, the aryl chloride, comes in, it undergoes oxidative addition, reduction with the manganese to generate our friend, the nickel 1 aryl, CO2 insertion to generate our carboxylate, and then this weird reduction and transmetallation step to generate the nickel 0. Now, this mechanism is extremely frustrating because we have all of these additives which are required in the reaction, and none of those additives are captured in the mechanism. So you're not sure what the additives are doing. It also has several unusual steps which have little experimental precedent, such as this CO2 insertion into the nickel 1 aryl. So we wanted to apply a mechanistic study to design a better system. We used the same trick we'd used for cross-coupling. Let's first look at nickel precatalysts in the same oxidation state as what is proposed in catalysis. So we put in nickel 2, nickel 1, and nickel 0. In all cases, we tried to keep the ratio of triphenylphosphine to nickel as being 4:1, so sometimes we added exogenous triphenylphosphine. And what we saw was that nickel 2 and nickel 1 gave us the same catalytic performance. Nickel 0 gave us decreased catalytic performance. And this was particularly troubling to us because by NMR, we could see that when we used these nickel 2 and nickel 1 precatalysts, our resting state was tetrakis triphenylphosphine nickel 0. So what is the difference between these three reactions? We hypothesized that when you start with nickel 2 or nickel 1, you need to reduce the precatalyst from these oxidation states down to nickel 0. And the manganese does this. And when the manganese does this, you generate manganese dichloride. Maybe manganese dichloride actually plays an active role in the catalytic reaction. When we add manganese dichloride to our nickel 0 system, we get back to the same yield as what we have with nickel 2 and nickel 1. So manganese dichloride assists in the reaction, and if we construct a hierarchical diagram, we can say that manganese 0 is not only an electron source, it's also a source of manganese dichloride. This implies that one of the reasons people may not have been able to use other reductants is the byproduct of the reductant is required for catalysis. So maybe we could use other reductants, for example, homogeneous reductants, if we also added manganese dichloride. The homogeneous reductant we decided to look at was this DMAP OED. So it's an organic electron donor. It comes from John Murphy's group in the UK. It has approximately comparable reducing power to manganese, so it has the required reducing power to do the reaction. When we do the reaction with DMAP OED, if we use the standard conditions, or the conditions shown here, where all I've done is replace manganese with DMAP OED, my product yield is less than 1%. One of the reagents that's required under the Tsuji conditions is triethylammonium iodide. When I remove the triethylammonium iodide, my product yield goes up a little bit, 7%, but it's really when I add manganese dichloride that I can use this homogeneous reductant and get a good yield of my product. And I don't need triethylammonium iodide. And we think the role of the triethylammonium iodide is to act as an electron transfer mediator between the heterogeneous manganese reductant and the homogeneous nickel catalyst. So when I use a homogeneous catalyst, I no longer need that electron transfer mediator. So DMAP OED now allows for decoupling of the role of the reductant as providing electrons and the manganese dichloride source. So it would seem odd if manganese dichloride is the only kind of metal salt that could promote this reactivity. And with DMAP OED as my reductant, I can probe that. So here is some data for that. Manganese dichloride gives the same yield as lithium chloride or lithium bromide, which are obviously much more desirable to use. They're cheaper, etc. Lithium triflate gives a reduced yield, suggesting that the halide is important in these salts. But if I use tetrabutyl ammonium bromide, my yield takes a further hit, suggesting that the Lewis acid, which is the alkali metal salt, and the halide play distinct roles in catalysis, but they have a synergistic effect. So you need both of them. So now if we look at manganese, we can construct an even more complicated hierarchical diagram where manganese is an electron source, it's a manganese dichloride source, it's a Lewis acid source, and it's a halide source. How do these affect the elementary steps? So if we go back to the mechanistic cycle I was presenting you, which of these elementary steps are aided by the presence of these additives? The step we decided to explore was this CO2 insertion, which people hadn't really understood. Part of the reason people hadn't understood or explored was it was hard to access nickel-1 aryl species. In the second part of this talk, we said we were able to synthesize some nickel-1 aryl species, so this also allowed us to look at this reaction. In this case, we make the molecule with triphenylphosphine ligands because that's what's required in catalysis. And this molecule is very unstable. It probably decomposes in less than 30 minutes at room temperature unless you have excess triphenylphosphine present. This probably explains why in the catalytic reaction people use excess triphenylphosphine. It's to stabilize this very unstable intermediate. It will react with CO2, and after we work it up with acid, we see the carboxylic acid in about 80% after 5 hours. If we do the same reaction in the presence of a Lewis acid, lithium PF6, and then we work up with acid, it takes 20 minutes and we get an 80% yield. So the Lewis acid, we think, is helping with the CO2 insertion step. Both of these reactions are very frustrating for an organometallic chemist because you'll notice we have unknown nickel in both cases. We don't know what the fate of our nickel is. When we do the same reaction with lithium chloride, we are able to work out what happens to our nickel. It goes to this nickel-1 chloride, and we have a precipitate present, which we think is the lithium carboxylate. When we treat that with acid, we generate the carboxylic acid. And we think that in the absence of a halide, the putative nickel-1 carboxylate, which is formed from CO2 insertion, is very unstable and undergoes a comproportionation reaction to generate nickel-0 and nickel-2. So having a halide present stabilizes a very reactive intermediate in catalysis by forming a nickel-1 chloride, which is more stable. So this is kind of a revised mechanism. It looks quite similar to the one that was proposed by Tsuji, but we now have this Lewis acid-assisted CO2 insertion, and then we have a transmetallation step where the nickel 1 carboxylate goes to the nickel 1 chloride, which is then reduced by manganese to generate the nickel 0. And if you don't have the halide, this nickel 1 carboxylate decomposes, and as a result you lower your catalytic yield. If you don't have the Lewis acid, then the rate of this process is slower, and this nickel 1 aryl, which is also very unstable, decomposes. So this is all of the things that manganese is doing in this reaction. So one very simple reagent is doing a lot, and this was part of the reason it was so hard to optimize these reactions to use other reagents. So now that we know this information, can we run this reaction under more favorable conditions? So first, we changed our ancillary ligand from triphenylphosphine to DPPF. This was just based on some catalyst screening. We have some ideas for this. But more importantly, we can run this reaction in THF using our organic reductant. Why can we run in THF when you can't using manganese? Because manganese dichloride is not soluble in THF. So it precipitates out of the reaction. We know that you need manganese dichloride to assist in the reaction, so it fails. Here we're using lithium chloride, and we can get good yields when we use our homogeneous organic reductant in THF. These types of ortho substituted substrates are problematic using manganese, and we think that's because the steric bulk prevents efficient electron transfer from the heterogeneous reductant to the homogeneous catalyst. When we're using a homogeneous reductant, we think we have simple outer sphere electron transfer, so the sterics are no longer a big problem, and we can couple these types of substrate in good yield. Additionally, I said earlier that Ruben Martin had extended reductive carboxylation to a wide variety of substrates. He typically needs manganese or zinc. We can take our optimized conditions, put in one of Ruben's catalysts for a different substrate, and show that we can replace the heterogeneous reductant with our DMAP OED. So now we're doing a reaction with an sp3 hybridized substrate, and all we've done is taken Ruben's conditions and swapped out the heterogeneous reductant for a homogeneous reductant plus the salt additive, and we get about the same yield that Ruben saw in his system. We also think that these types of reactions or these types of mechanistic conclusions we've made will be general to other types of cross-electrophile couplings. So the types of reactions that Dan Wykes has pioneered at Wisconsin, Sarah Reisman is doing in an asymmetric fashion, they all need additives, they all need heterogeneous reductants. And in preliminary work, we've shown that we can use this strategy to do those transformations in high yield. So if we look at this nickel-based system for reductive carboxylation, what we've done is we've taken a system which needed excess additives, restricted substrate scopes, undesirable amide-based solvents, and superstoichiometric metallic reductant. And through our mechanistic studies, we've resulted in this kind of diagram from this kind of diagram, where we have an improved precatalyst, expanded substrate scope, synthetically desirable solvent, and we use a stoichiometric organic reductant. And this organic reductant, DMAP OED, will shortly be commercially available from Sigma Aldrich. It is, I would say, not the optimal reductant. It's quite air sensitive, and it's not as cheap as we would like, certainly not compared to manganese. And we're currently working with Merck to try and design improved organic reductants which will have the same properties but be cheaper. So with that, I'd like to finish with one conclusion which really summarizes our approach to designing new catalysts through a sort of short quote. So that is that turnover records are temporary. Someone will always develop a catalyst which gives better activity, better stability than you. We want that. We want progress to be made. Society, as Umicore can attest to, loves catalysts. They are crucial for our productivity and for future sustainability. But from my group's perspective, if we do a good mechanistic study, the conclusions to that will be forever. Thank you very much.